Hello, and welcome to Risc-V emulation in a high-level language. Last time, we wrote a program that read the command line arguments and attempted to write them out just like the echo program does. Unfortunately, that program didn't work very well. It crashed immediately on our first try. And so we're now faced with the amazing prospect of having to debug this Risc-V program when we don't have a debugger. There's no insight. So we have to solve this problem using what tools we have and what tools we can make ourselves. So, well, let's jump straight into this and see if we can figure out what is wrong with our code. So here's our program, and let's try running it again just to refresh ourselves on what exactly was going on. So here we see the crash. The immediate cause of the problem is that we're trying to read from address. Let's see, what's the value of the address? This address. And if we display this address in hexadecimal, uh, it is at address 80000 BC. And if we look at the range of bytes that we're trying to access, we will see that that range of bytes is only BD bytes long. So we're reading off the end of memory. And of course, that should give us an exception. But what's going on? What are we trying to do when we run out of memory or read out of bounds? We're trying to load a word, and the load that's is happening where? It's happening at IPTR, so at address 38, whatever that means. So our problem now is that I have no idea what address 38 is. The assembler has been doing its job assembling my program and placing these instructions at their addresses, but I have no idea how to map one instruction to the other. What tool could I possibly use to help me resolve this issue? Well, we do have this commented out statement, which, if you recall from earlier episodes, it dumps the current instruction pointer and then the bit or binary representation of the current instruction. Now I'm going to be using something similar to this to try to identify individual statements. But I'm not going to bother with the instructions because we should be able to follow the flow of our very simple program just by looking at how loops and other values are consumed or generated in this program. So let's start by writing a console.writeLine, and we'll use the same format as before, where we say this is our current instruction statement, just like that. So this will, for every instruction that we emulate, we will first write out the address that we're currently at. So let's see. So let's also take a look at the input and the output. So the input is this command line that we spent so much time last time building up, and it looks okay to my little eye. I notice that the strings are located here. This one was located at address 400FF3, and I can see the pointer to it over here at 40FE4. So that looks good. And then at address 4FE8, we see the next pointer that ends with F9, and F9, of course, is right here. So I am fairly confident that this array is correctly constructed. And I have further evidence to that because I can see how the first word, hello, was successfully printed. And if I look closely, I notice that the space following the hello was also printed out correctly. Now, the extra space is written inside the main loop. So if we go back to the main program, we'll see that the space is written here in the main loop. And so we know that this piece of code works, but then when we try to enter into put string, and try to print the next word, it blows up. So let's note down a few important values. And I'll open up a new window to do this. We'll want to write down the addresses of our strings. So we know that this is the beginning of our vector of pointers. And inside that vector of pointers, the first pointer is 400FF3, which is argv of 0, the first pointer. And then the second one, 400FF9, is the second pointer. So that is the data that constitutes our command line. All right, let's go back to the program now. Another thing that we could do to chase this is to see whenever new values are written. That will be helpful because then we can see things like when we're loading the registers from memory, we'll see how those bytes that we're reading from memory get loaded. So let's find the emulator, and in the emulator we will look at write register, and in write register we can see the values that are being written into the register. So that this will be very helpful. Now there are times when we are writing to register 0, and register 0, as we know by now, is that magic register that ignores uh, all writes, and it always returns a 0. And the way this is guaranteed is by this mask mechanism. So we can let's ignore writes to register 0 because they're not going to be interesting for our analysis. I will just say that if the mask is not equal to 0, then we will do a console write, and we'll write the following. We will write that the register DST was just assigned a value like that. All right, now let's run our program and see what the resulting output looks like. And yeah, there we go. So here we see in the output window, we see the variable x13 updating. Interesting. Why are we not always seeing the... Oh wow, this is unexpected. It looks like the console write is not always happening. Let me... Oh, write line maybe? Let's try that. See if that makes any difference. That's more like it. I wanted to have it in alternating lines. Okay, so this is our output now. It's a log trace, and it's going to be painful, but we don't have a debugger right now, so it's much finding problems is going to be a lot harder if we don't have the nice tools for it. But we'll be able to find this, I'm pretty sure, just by being patient and being methodical. We'll be able to to figure out what the problem is. So let's hop over to that window that we had here, and we'll paste in the trace. And let's look at the program in this other window to see if we can correlate what's going on the left side with what's going on the right side. So all right, I'm trying to get rid of all these red colors. Maybe if I save this file as... Maybe that will... No, didn't shut it up. Okay, I guess we'll have to live with these colors. Let's not be distracted by them. So, okay, we'll start here. So this is the start of our program, and the very first thing that we do is we update x2, which, as you should recall, is now the stack pointer. So initially we had a stack value of fd4, and we then subtracted fe4. So we were pointing here. which is right at the beginning of our argument vector. And then we subtract 16 from the pointer. So the new value is now ffd0. I'm sorry, e0 and d0. So this allocates the 16 bytes for x2. All right. And then we store a bunch of values. And then we jump to the loop test function, which is, if you look at the addresses that we're visiting, suddenly we jump from 14 to 48. That is this jump to the loop test. And what does the loop test do? It loads a word into register 13, and that's what we're seeing here. So we're loading the the index into register 13. And then the next statement is we're loading the argument count because we want to perform this comparison. And if the comparison is true, then we go to the loop body. And that's exactly what happens. We see how after we reach address 50, this is the address of the branch. We now are at address 18, which is this function right here. Now, this is going to call, it's going to check to see whether I is 0, and if it is not 0, then we are going to skip the writing of the space. Okay, that's good. So that's what we expect to happen here at address 50. We load register 13, and then we skip some code. Notice that the gap between these two instructions is 10 bytes, so that means that we jumped over 3 instructions, bam, 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 those 3. So now we're down here, and now we're about to write the first argument. So what we do is we load x10 with fe4. Now that's our argument vector, if you recall our vector of pointers. So now we have a pointer to the list of pointers. And then we grab our index, x13, and then we multiply it by 4, which is what this statement does. And of course, 0 times 4 is still 0. And then we add those two together to give us the resulting slot in the array of pointers, which is this x10. That happened over here. And then we read the value of that slot into x10. And now you see ff3, which should be familiar. That's the first pointer, the one that is pointing to this word hello. So now that we have that pointer in or in x10, the register, the argument register, we now call the function putString. And here we see how x1, which is the link register or our return address, gets updated with the value 40, which is the address after 3C. So this must be the jump and link instruction. And what we're doing here is we're writing the value of the next instruction, which is this increment or add instruction, right before we jump to the putString function. So at the start of the putString function, so that would be down here, we increment the stack pointer or decrement the stack pointer with 8. So that's what happens here. So let's annotate our trace a little bit here. This is the putString. And here we on entry it has the value fd0. So I'll write x2 equals fd0, and we saw that happening up here. So it has the value fd0. And then what we do is we increment or decrement it by 8 to give us some space for our two register values. That looks good. And then we're going to call the string length function. So we look for another discontinuity in the addresses, and look at that. Here's a big gap. So this means that this is the call to strlen. And x2 is, well, unchanged. It should be 00400fc8. Okay. And then we have to go through the strlen function, and here we notice how it first reads in 68, which is a lowercase h in ASCII, and then a lowercase e, a lowercase l, another lowercase l, another, or then an o, lowercase o, and then finally the terminating 0, which should stop string length. And the string length then returns to the caller with the number 5. That's the number of bytes in our string, which is what we wanted to find out. Now we see a discontinuity in the in the address of the instruction that we're executing, which means we're now back in put string. And so now we have to shift over the value that we had in x10 over to x12 because that's where the write system call expects it to be. So this is the add I that we see here, which is a copy. It copies x10 into x12. Okay, that looks good. And then in x11, we now have a copy of the pointer to the string, which is done by loading the pointer from the stack. Remember that we saved it in the stack here, and now we're restoring it from the stack, but we're storing it into a different register because the write system call expects it in register 11. And then we also have to indicate that we want to write to the standard output, which is this handle number 1. And finally, we select the write system call, which has the number 1. And then we issue our eCall, and then we see hello appearing in our output. So that looks good. Okay. And then at the end of all this, we are now ready to restore and return back to our caller. And so here we restore our caller's link address. So this is the address that we want to come back to. This instruction right here is causing this update to happen. So we're returning back to address 40 as expected. But here there's something fishy. Our function is supposed to restore our stack pointer to the value that it had when it came into put string. But let's take a look at this. When we came into put string, our stack pointer was fd0. But now, when we reach the return of our function, after performing the add here, it's still at fc8. So we did not restore it to fd0. And so now our stack is unbalanced. And that is very likely the cause of the crash, because now our stack is all screwy, which means that nothing is where it's supposed to be, and we're going to be reading invalid data from the stack. And of course, if you look at the program, it's fairly clear what the problem is. If you're experienced, this will be a glaring oversight. But for a beginner, this might be confusing. What went wrong? Why didn't it increment the stack pointer? And the reason why is because we did not use the correct assembler instruction. This is the add instruction, which adds two register values together. So this would read the value 2 or the value out of the stack pointer, register 2, but then it tries to, it reads the value out of register 8. But we don't want to read the value out of register 8, which happens to be 0 at this time because we haven't used it. So the end result will be that it just doesn't change the stack pointer at all, which is not what we wanted. What we wanted is to add the literal number 8 to register 2. So by adding an I here, we correct the bug. So now what we'll be doing is actually adding the constant number 8, not the value contained in register 8, to register 2. And that gives us the updated stack pointer, which should now have the correct value. So if we run our program now with our bug fix applied, we no longer crash. Unfortunately, we can't see the output because it's flooded by our diagnostic output. But let's go ahead and comment out the diagnostics, and let's see if we can get to see the expected output from our program. So let's stop the debugger and start it again. And there we have it. Hello, space world. So we have now fixed our bug and we have now finally produced our program. But the, the experience of doing this was, debugging this was quite unpleasant. We had to do a lot of manual groveling around, and it's very hard to understand exactly what the program is doing. So one of the things that we could do is to implement a very, very crude and rudimentary uh, disassembly step to help us understand what is going on with our code. And the way I'm going to do this is I'm going to be using the Reco decompiler runtime library to do this. And it's intended for precisely this kind of usage. So why don't we add a little bit of more friendly debugging support here so that we can see what's actually going on. So rather than doing this, I'm going to add a line called dump current instruction here. And let's implement this method. So we still want to display the current line, but before we do that, we want to disassemble the current instruction. So we need to use the disassemble provided by Reco to obtain the sort of human readable version of the bytes that are constitute the instruction that we're executing. So how do we do this? Well, um, this is this is what we do. We need to talk to the Reco runtime and grab an instance of what Reco calls an architecture class. So let's just do this. We'll say that the architecture that we want is now a Risc-V architecture requires a service provider, but we're going to cheat and just pass in null here. We're going to give it an archive or architecture ID, and then we're going to give it an empty set of options because right now we don't really care to switch the CPU to 64-bit mode. So we're happy with this. That creates an architecture. And then we also need to create a piece of memory that this architecture can disassemble. And it requires the memory to be in a specific format. So what we'll have to do is we'll have to read the bytes out of memory and store them into another chunk of memory that will feed to Reco. So the way we do that is we say, let's see, we'll want to get to our memory. And so we go to our memory and we say get span. And actually what we want is the current instruction pointer, not the actual instruction bytes themselves. So let's go back to the caller and pass in IPTR instead. There we go. Good thing we caught that. It would be an ironic if we had a bug in our debugging code. Okay, so now we ask for the bytes at that address and give me 4 bytes, please. And I want to read them. And this needs to be cast on integer. And so now we have a span. And now what we need to do is create a chunk of memory and copy that span to the chunk of memory. So we'll say bytes equals span, a new byte of 4. And then what we'll do is we'll say span copy 2 bytes as span. So this will copy the bytes in the span from our memory into the small local chunk of memory that we're going to be using for our disassembly. Now we have to build an object called a memory image. So we'll say mem, well, we already use mem. Let's call it m, byte memory area. And we need to give it an arbitrary, we need to give it an address. So we'll need to specify the address. I put her. It's a 32-bit address. And then we also need to specify the bytes. Great, so now we have a memory area. The next step is now to provide the architecture with a stream abstraction on top of this memory area. So what I'll do is I'll say var rdr equals m.create little endian reader. So we want to create a reader that reads bytes from this memory area starting at offset 0. So starting at offset 0, the disassembler will read that first byte, or the first 4 bytes. Now we're finally ready to create the disassembler, so we'll create a disassembler, and we tell the disassembler, or the architecture, please create me a disassembler, and use the following stream to read the data. And then we ask the disassembler itself, give me the first instruction. And this is a link call, because a disassembler is just an IEnumerable of machine instructions. So this will give me the first instruction, and we'll call that inster. And now we're ready to print this out. So we'll print it out like this. Okay. And then we're done. So if we try to run this now, let's see what happens. Hopefully I've gotten everything working. And look at that. Beautiful, beautiful output. So if I had done this from the beginning, then let's reintroduce the bug. It was here. If I were to run this program again now, we see that the crash is happening at this instruction. And of course, another helpful thing would be to provide the values of all the registers at each step. But we're not going to be writing a full-blown debugger in 1 hour. We've just added a little bit of friendly support that will help us troubleshoot issues in future installments of the series. So we've fixed our bug. Well, actually, let's go back and undo the undo. So this is an add-I. Now we fixed our bug. And now we have a program that actually performs something useful. It performs the echo operation. So we can now change our program so that it has more arguments. Let's give it a few more. And if we run this, let's also turn off the tracing while we're here. Oop, it doesn't seem to have compiled my code. Interesting. Interesting mystery. Do we have another bug? It looks like we have another bug, because hello and world and another argument are correctly in our command line. It's writing 2 words. Ah, okay, well, so let's make use of our newly gained powers to see what the problem might be. Let's turn back on the tracing of the instruction, but also let's find and write register the places where we're updating our registers. And let's see if we can figure out what the problem is here. So there are 4 command line arguments, and these pointers, E2 points correctly, E8 points correctly, EF points correctly, and F7 points correctly. So all of these pointers look correct. So the data looks fine. All right, let's run the program and see what happens. So I'm going to copy this into our buffer here. And let's see what's going on. As you can see, our trace is much longer now because we're calculating the lengths of all those strings. So first of all, let's see if we actually get to all of the arguments. Here is the L. Okay, so here are the letters E, L, L, O. This is lowercase o. And then we will see the exclamation point, which is a 2, 1. That is the lowercase d, and then the exclamation point of the word world. And the next thing that we would expect to see is a lowercase a, which is 6, 4, but we never do. We just stop after 2 iterations. So whatever is controlling the number of iterations that we execute is tripping. So let's take a look at the main loop, and let's use the program as a reference again just to see what we're doing. But so we're supposed to have the argument vector, and the argument count is supposed to have the correct value. So let's see what happens when we load the argument vector for the first time, and that happens when we check the loop. So these are all the store instructions. Then we go and do the jump. So that jump here corresponds to this jump here. We have to go to the loop test now. And the loop test, we say load something from register 13, and we get a 0. And there's our 4, so that is correct. So now let's take a look at the next time we hit statement 4.8. And let's see what value x13 and x10 have then. So here x13 has the value 1 and 4. Whoa. X13 suddenly has the value 5. And now I know what the problem is. So the problem is this. X13 is a register that we're using to compute I, but we're also using it to compute I times 4. And by making this computation, we trash I13. So we can't use this instruction SLLI to both keep the variable I, which we need in order to perform these comparisons correctly, but we also need the variable I shifted by 4 in order to correctly compute this address. So we'll just use another register for now. We'll use register 14, which we're not using anywhere in our program, and then we'll use it in the calculation of our address instruction. I hope that made sense. So we realized that this register 13 was doing dual duty. We were using it for our index variable, but we were also trashing it here, computing the index variable times 4. So let's change this so that it reflects correctly the operation that we're doing. And now, if we remove our debugging code, we have the expected results. All right. So at this point, we have an emulator that can read command line arguments. It can perform file I/O, and it can emulate a big subset of the Risc-V instruction set. So at this point, we have a functioning virtual machine. Now, it's got its flaws. It's certainly not ready to be used in any production environment, but the direction I'm taking this series is more on the educational focus and rather than high performance. Naturally, this emulator could be tuned to make it faster, improve its performance in many different ways. But for now, I want to keep the code clear because the next step is going to be a rather big piece of surgery to our program. And to give you a little foretaste of what's going to happen, let's go back to our main program class here. So this program that we have here is asking the user to use an object called an assembler and then we're making function calls or method calls on that object to build our assembly language program. However, I think that uh, this is a little bit verbose. There's a lot of overhead in this programming style that we're using here, which is basically C sharp. And if you have experienced assembler language programming f- from from other sources, you will quickly recognize that this is not the normal way that people write assembly language programs. Instead, what happens is you write a separate file, and then inside that file, the words or the, the commands or the text that you write doesn't look like this. As an example, what you would probably write in an assembly language program would look something more like this. So if you compare these two lines, you'll see that this is somewhat less typing. So what we would like to do then is to reduce the amount of typing that you have to do to uh, to something a bit more palatable. We're going to create a new assembler. And what this assembler will do is instead of asking the programmer to issue these method calls, the programmer will instead write his source files in a separate text file. And what we'll do is we'll break out the assembler and linker into a separate program, and that program will consume a text file that contains assembly language instructions and then generates an output file, which this emulator program will then load in, just like your operating system loads in an executable file and then executes the instructions in that in that executable file. So there's a lot of material to cover. It's going to be divided up into multiple chapters. But the next step that we'll do is we'll write an assembler, a text assembler that will be able to read files from the file system and then generate an output file that can be loaded and executed by our emulator. But that work will have to wait until next time. So until then, keep hacking. I hope you're enjoying this series and stay safe out there. Bye.